Hello everyone, welcome to YouTube channel Energy-Exergy Theory Applications. I am Professor Tatiana Morozyuk and I am the author of this YouTube channel. Today we are with the topic exergy. All lectures have a very dynamic style of presentation. Definitely some of you would like to learn more, particularly about exergy. We will be happy to answer your questions and provide with an extended information. Our contact email you can find in the description of each video. Please support our work with a like to this video, subscribe the channel and share the link with your colleagues. Today we continue with the exergy analysis, and today the part 3 of the very big topic exergy analysis. As usual, I would like to repeat some definitions and also some statements for each topic, including exergy analysis. So exergy, basic thermodynamic analysis, or easier to say exergy analysis, we need to define location, magnitude, and causes of thermodynamic inefficiencies. And thermodynamic inefficiencies within the system associated with exergy destruction term and term of exergy losses. The term of exergy destruction, it is a description of irreversibilities. Usually, it is very easy to understand what means irreversibilities within each component. But the term exergy losses, which associated with exergy transfer to the environment, very often it is quite complicated issue, and people would like to have a little bit more information how to treat exergy losses. So, by other words, the key topic for our lecture today, it is exergy losses. Exergy losses for the overall system. We will not discuss particularly losses for the components. That will be our another lecture will be dedicated to that. Today we will discuss still exergy analysis on the system level. And we already learned from the previous lectures that we can conduct exergy analysis in the terms of in-out exergy, but it is old version of exergy analysis and not will give us not appropriate definition of efficiency, exergetic efficiency, and better to conduct analysis in the terms of exergy of fuel, exergy of product. So regardless which method we will apply, old method of exergy analysis or a new method of exergy analysis, the term of exergy destruction will be the same. So irreversibilities will be defined absolute correct using two different methods. But the term of exergy losses, this should be discussed. Because if it is just in the exergy analysis applied in the term of fuel and product, then exergy losses, it is one cumulative term as all other terms. But if we discuss exergy analysis, or we would like to discuss each incoming, outgoing streams, exergy streams for the system, then we need to find out what is it losses. Exergy losses, it is only one stream outgoing of the system, or maybe it is incoming to the system, or maybe it is the difference between in and out. So this we will discover today. And also we will discuss some cases when exergy losses are charged to exergy destruction. We already mentioned this possibility, and with emphasis on dissipative components within the system, how we can treat dissipative components, and also exergy losses, how can be connected to the term exergy of fuel. So actually we also will revise the term exergy of fuel for different applications. And today, three energy conversion systems, very general energy conversion system, will be under evaluation. First, it is heat engine. You know, it is the general term of all power generation systems. We will discuss refrigeration machine. That system operates at the temperature below of the environment with inverse thermodynamic cycle, and also heat pump. It is also inverse thermodynamic cycle, but system operates above temperature of the environment. And definitely exergy losses, since it is heat transfer or exergy transfer, better to say, to the environment, definitely will be associated with the processes that are taking place around temperature of the environment. So let us repeat some basic equations from the energetic analysis for this energy conversion system, and also emphasis will be given to exergy analysis. So now we are with heat engine. So just thermodynamic concept, and we know that driving energy, I emphasize energy, it is heat supply to the system. Positive effect, it is W net work generated by system, and heat transfer to the environment has no special term. It is just heat transfer to the environment and definitely participated in energy balance. Now, exergy analysis. Exergy of fuel, it is exergy transferred to the system. Exergy of the product for power generation system, heat engine, definitely it is work generated by the system, and exergy transferred to the environment, it is the term of exergy losses. Now, refrigeration machine and heat pumps. Energetic analysis quite similar. Driving energy, it is power supplied or work supplied to the system. A positive effect for refrigeration machine, it is refrigeration capacity. For heat pump, it is heat generated within the system. COP value we also know, but now exergetic analysis. For refrigeration machine, exergy losses, it is heat transfer to the environment from the condenser, similar to power generation systems. But for heat pump, exergy losses, it is heat taken from the environment. This is very interesting. For heat pump, heat taken from the environment, it is not the fuel of the system. It is losses of the system. And for heat pump, fuel of the system associated only with the work supplied to heat pump. If it is compression heat pump, then it will be work supplied to compressor. So now let us discuss two cases. Power generation system, we will use Rankine cycle as the simplest example of power generation system. So I will not discuss the working fluid of Rankine cycle. It is just four components: steam generator, turbine, condenser, and the pump, basic Rankine cycle. And we will discuss also compression refrigeration machine, also the simplest technical solution. It is evaporator. So evaporator is here, compressor, condenser, and throttling valve. It is a little bit unusual drawing of refrigeration machine. That's why we can a little bit mix up the components. So one more time: evaporator, compressor, condenser, and throttling valve. And now the term of exergy losses. For Rankine cycle, for power generation cycle, condenser, from condenser heat is transferred to the environment. For refrigeration machine, also heat transfer or exergy transfer to the environment is taking place within condenser. So exergy losses for us, it will be associated with condenser of Rankine cycle or condenser of refrigeration machine. So now let us start detailed discussions with refrigeration machine, because it is a little bit simpler. So for our analysis, now refrigeration machine is simpler, but usually refrigeration machine is much more complex. Okay, so let us discuss an assumption that all components are productive. I would like to bring your attention that throttling valve within refrigeration machine is a productive component. To treat throttling valve as a dissipative component within refrigeration machine, it is a mistake. So therefore, throttling valve we will treat as productive component. So what do we have for refrigeration machine? We have refrigeration capacity or exergy of the product to store the product. It is exergy at stream 6 minus exergy at stream 5. Please remember that for refrigeration, we are always working below temperature of the environment. Then the lower temperature, the higher exergy. Therefore, it will be 6 minus 5. And work supplied to the compressor, it is stream associated with the fuel, and exergy of work, it is work itself. Therefore, we have definition product and fuel. One more time: if all components are a productive component, we have equation for the total exergy destruction within the system. Now the equation: if condenser will be treated as dissipative component. We can do it also because exergy transferred with heat transferred from the condenser, it is to the transfer exergy of the environment. So also condenser can be treated as a dissipative component. Then we don't need to have information about stream of cooling media coming to condenser. So we don't, sometimes we don't even need to simulate, so to calculate properties of streams 7 and 8 for cooling of condenser. We don't need to calculate exergy of these streams, so actually we can fully subtract this stream from the simulation and from the analysis if condenser is a dissipative component. And then we can say that losses of the overall system will be zero because these streams are not considered, but losses will be charged to distractions. Therefore, also equation for total exergy distraction within the system will be absolutely the same as in previous case, but term of exergy distraction within condenser will be calculated differently. Since condenser is a dissipative component, it is only exergy in minus exergy out, exergy as stream 2 minus exergy as stream 3, and that's it. So now we have no losses of the overall system because losses of the overall system are charged to distraction within condenser, and condenser is a dissipative component. For my own research, I never treat condenser as a dissipative component for simple refrigeration systems, because in this way we will miss information about irreversibilities within condenser because of heat transfer, and we cannot improve condenser. So therefore, if we are dealing with system with relative small number of components, it always makes sense to treat condenser as a productive component. But if it is very complex refrigeration machine, and these cases we will discuss a little bit later, then it is meaningful to treat condenser as a dissipative component because it will not really affect to the evaluation of the very complex refrigeration machine. So now let us proceed with the Rankine cycle. With Rankine cycle, we have quite a lot of very interesting discussions. So we have, I repeat, very simple power generation system. We have steam generator. It also can be called boiler or any other terms that use it in all books. We will say steam generator. This is a better modern word. After that, we have turbine, we have condenser, and we have pump. So if all components are productive, then fuel of the overall system will be the difference between exergy of stream 15 and stream 16. So this is heat transfer also will be calculated as enthalpy 15 minus enthalpy 15. So here in exergy terms, I repeat, and exergy 15 minus exergy 16. Product of the system, it is the difference of work generated by turbine and work required by compressor. So it's so-called W net. All components productive, I repeat, then losses of the overall system, it will be the difference between stream 14 and stream 13. So this is cooling water or cooling air, and later this exergy will be transferred to the environment. Similar to refrigeration machine, we can say that condenser is a dissipative component, then streams 13 and 14 will be removed from the simulation and from the analysis. Absolute the same situation as we just discussed for refrigeration machine. And we have equation that exergy losses of the overall system is zero, and exergy losses of the system is charged to the term of exergy distraction within condenser. Condenser is dissipative component, exergy in minus exergy out, and we are done with the exergetic analysis of Rankine cycle under these assumptions. But also very interesting that we can treat condenser as a dissipative component, but differently. We can have different kind of analysis, but also correct. We can put together in one evaluation, so with boundary conditions, we can put these boundary conditions simultaneously on productive and dissipative component. That was a very common approach very many years ago. Now it is not very often used, but nevertheless, you should know that this approach also exists. We can develop a new block condenser and turbine simultaneously. And this is like a block component. So many components can be together as a black box, for example, components. And we can say that this block is productive. So two components will be together productive block. So then exergy losses of the overall system will be zero because no exergy transfer to the environment. And exergy destruction, we will have only three components. We will have block, turbine, and condenser. It is one block, like a one component. We have exergy destruction within pump and exergy destruction within steam generator. Then how we should treat this component? For exergy destruction for this block component, it is fuel minus product. Fuel of this component, it is the differences in exergy stream 9 and 11, and product will associate only with work generated by turbine. So this approach is also possible. It is not mistake. It is also possible, but with this approach, if we will conduct exergy analysis like that, definitely we will miss a lot of information how to improve turbine and how to improve condenser. So one more time, this approach is working very properly for very complex energy conversion system, when such a block component will not affect to the deep look to the system, how to improve the system. If it is simple Rankine cycle, I cannot recommend this approach because we will miss quite a lot of information regarding turbine, for example, how to improve turbine and how much we can improve turbine. And now let us continue with Rankine cycle, because now we will not discuss condenser. Condenser can be treated differently. We just mentioned all these options. But now let us discuss about steam generator. Now, how heat is transferred to the steam generator and how exergy should be treated, what means exergy of fuel for the steam generator. So I will repeat, if it is energy analysis, for us, the only interest enthalpy 15 minus enthalpy 16. If it is exergy analysis, we have quite a lot of options. Let us assume that heat, stream 15, is generated somewhere. So before our energy conversion system, somewhere there is another energy conversion system with some processes, and we will take stream 15 from this energy conversion system. We will use this stream from state 15 to state 16, and after that another energy conversion system will continue to use this stream. So our responsibility, it is only to use exergy from state 15 to state 16. Then fuel of the system will be 15 minus 16, similar that we discussed it before, and losses of the system will associate only with condenser if condenser is a productive component. For example, such a case very often can happen if we discuss about use of solar energy or geothermal energy, or maybe sometimes waste heat, because in this way really Rankine cycle or organic Rankine cycle is a particular case, can be in the middle of very complex energy conversion processes, let's say like that, from one system to another system. Then fuel as 15, exergy 15 minus exergy 16 is absolute justified. Let us use more realistic case, that we will take stream 15 from energy conversion system and we will use until 16, but after that no one will use this stream anymore, and stream 16 will be rejected to the environment. Then for us, fuel of the overall system, it will be only stream 15, and stream 16 will be already losses of the overall system. Again, condenser can be treated differently, productive or dissipative, but 16 definitely will be associated with the exergy losses of the entire system. Therefore, definitely exergetic efficiency now will be lower than in previous case, but it will be more realistic evaluation of energy conversion system. We know how fuel, what means fuel for this system, and how we should treat losses of the overall system. And we can have one more case, that heat, stream 15, will be generated within the system. It means that within the system, we will have not only 4 main components for Rankine cycle, we also should implement combustion chamber. Then irreversibilities within combustion chamber will be also charged to the total exergy destruction. So exergy destruction within combustion chamber will be charged to exergy destruction of the overall system. Actually, we have the 5th component. and stream 16 will be rejected to the environment, then fuel of the overall system, it will be exergy of fuel and exergy of air. So real fuel, it can be gas, coal, oil, whatever it will be. And definitely we need air for combustion process. And losses will be associated with stream 16 and depends on how we will treat condenser. So definitely all these three cases that we discussed will have different exergetic efficiency, exergetic efficiency of the overall system. And this case will have definitely the lowest exergetic efficiency. And I would like to repeat that all these cases that we discussed today are absolute correct to conduct exergy analysis like that. We cannot say that at least one discussion is correct and another not correct. No, everything is absolute correct. But this is how we can apply exergy analysis, and exergy analysis will give us absolute clear picture what happened within the system and how we can evaluate the system. But the same we cannot same approaches we cannot use for energy analysis. Energy analysis always energy in, energy out. But for exergy analysis, we can properly discuss exergy losses as inefficiencies within the system, but simultaneously with proper definition of fuel of the system. So this lecture we discussed system analysis. Next lecture we also will continue with the system analysis, but we will focus only the energy conversion systems that operate above temperature of the environment. And if you found this lecture interesting and useful, please give a like to this video, subscribe to the channel, and share the link with your colleagues. Thank you.